In my previous video, I built a DIY balancing machine for my RC turbine project. At that moment, I thought I had achieved the required accuracy, but I was wrong. When I checked my results against the ISO standard, I realized that my system was not even close to what is actually required for a high-speed turbine rotor. In this video, I'll show you why, what I got wrong, how I redesigned the system, and how I finally reached ISO level balancing accuracy using a low-cost DIY setup. Hi guys, I'm Alfonso. I've been an engineer in the space industry for more than 40 years, and now I'm sharing my passion for CNC hobby machines. For years, I've dreamed of building my own RC turbine engine, and now I finally feel ready to make it happen. To properly balance a turbine rotor, intuition is not enough. You must use the ISO 21940 standard. For this type of rotor, the required balancing quality grade is G0.4 at 120,000 revolutions per minute, and for a rotor mass of 80 grams, the maximum allowable imbalance is 0.0024 gram millimeters. That means only 0.00012 grams at a 20 millimeter radius. To put this into perspective, this is equivalent to a 1 millimeter diameter ball of sticky tack. This single number completely changed how I approached the problem. In my previous setup, I was only balancing the minimum turbine rotor. This time, I decided to balance the complete rotor assembly exactly as it will run in the turbine. That includes the shaft tunnel, ceramic bearings, and the nose nut. Only by doing this can the results be truly representative. The shaft tunnel is made from aluminum and requires standard machining accuracy. After machining Inconel 718 in the previous video, working with aluminium honestly felt like a vacation. The part was machined using a combination of lathe and milling operations. Next is the nose nut, also made from aluminum. Most of the machining is straightforward, but high accuracy is required for the magnet housing, since this directly affects the phase reference signal used during balancing. In a real turbine, high-quality ceramic bearings are used. However, using expensive final bearings during debugging is risky and unnecessary. So instead, I decided to build my own hybrid ceramic bearings, starting from a high-quality standard bearing. First, I remove the cage and disassemble the bearing. Then, I modify one face of the inner ring on the lathe. This allows the integration of ceramic balls. During assembly, I use grease in the outer ring to hold the balls in position. And here is the final result, a low-cost ceramic bearing suitable for testing and development. Now it's time to assemble the shaft tunnel. This must be done very carefully to avoid applying forces in the wrong direction, which could disassemble or damage the bearings. Because of the new shaft dimensions, the original tunnel support of the balancing machine was no longer valid. I redesigned the support and 3D printed a new one to maintain proper alignment and repeatability. In the previous version, I used an ADXL 335 accelerometer. This time, I switched to the BMI 160, which includes the ADC inside the chip, and offers significantly better noise performance. The sensor can deliver data at up to 1,600 Hz. However, bandwidth and output data rate are directly linked. Reducing bandwidth also reduces the number of samples per revolution. Because of this, most of the signal filtering must be implemented in the ESP32. For this project, I use a low-cost ESP32 clone that costs only a few euros. Communication with the sensor is done via the I2C bus, which is already close to its limit at this data rate. The BMI 160 also supports SPI, which would be more suitable, but I was not able to make it work reliably with this particular sensor module. This is the final balancer assembly, ready for testing. To spin the rotor, I use compressed air. I modified my air gun with 2 nozzles to apply a pure torque without introducing lateral forces. However, when I reduce the sensor bandwidth, the number of samples per revolution drops significantly, well below what is required for ISO quality measurements. This clearly showed that software processing would be critical. I improved the ESP32 software step by step. I started with a simple low-pass filter, similar to the one used in the previous version, but it was not sufficient. Then I implemented a second-order Butterworth low-pass filter, and finally a bandpass filter that removes both low-frequency drift and high-frequency noise. During this process, I discovered that achieving ISO quality requires an effective resolution of 1.6 lsb, while the raw sensor noise is typically between 3 and 5 lsb. The key solution was synchronous averaging, also known as a lock-in technique. The software detects a reference flag from the hall sensor. If the rotational speed is stable, one full revolution is stored in a buffer. Multiple revolutions are then averaged, and finally the amplitude and phase of the imbalance are calculated and displayed. The program outputs new results every 2 seconds. I leave the full software in the video description if you want to explore it. After studying extensive documentation, I found that the most reliable balancing method is the test mass method. I implemented the entire procedure in an Excel tool. First, I calibrate the system offset by placing a known mass at the reference position and measuring the response at different speeds. I discovered a linear relationship with speed, which I now use to correct the output data. First, I measure the initial rotor imbalance. Then, I add a reference mass and measure again. From these two measurements, I calculate the required correction mass and angular position. This sequence is repeated until the imbalance is below the ISO G0.4 requirement. I achieved this goal in only 2 iterations. The final imbalance is equivalent to less than a 1mm ball of sticky tack. This project has been an incredible learning journey. Sensors, ESP32 programming, signal processing, data analysis, physics, all of it comes together here, and I'm still only scratching the surface. Next steps will include dual plane balancing and exploring piezoelectric sensors. If you found this video useful, please give it a like and subscribe so you don't miss the next part of this RC Turbine project. Thanks for watching and see you in the next one.